In this episode of Home Theater Geeks, I talk about high-resolution audio and whether or not it's worth it. Check it out.
Podcasts you love.
From people you trust.
This is TWiT.
This show is brought to you by members like you. Thanks.
Hey there, Scott Wilkinson here, the Home Theater Geek. Today I'm going to talk about high-resolution digital audio. Now, when CDs first came out, they were touted as perfect sound forever. However, many thought that they were actually pretty cold and harsh sounding. So, while there is certainly a debate about whether or not digital audio or analog audio sounds better, one solution for the digital audio crowd was to, well, maybe we can increase the sample rate and or the bit depth of the digital audio and see if that would help. That is generally called high resolution audio, anything that exceeds the specifications of CD audio. So I wanted to start with a short explanation of what digital audio is, in case anybody out there is unclear on the subject. So we start with sound waves. That's where it all starts, right? And any complex sound wave, any sound wave at all, can be broken down into its constituent parts, which are the simplest sound of all, called sine waves. And these constituent sine waves all have different frequencies and amplitudes, but when you add them all together, when you combine them all together, you get the complex waveform that you were originally listening to. So in order to get a waveform, a sound wave, into the digital domain, you have to digitize it. And that involves analog to digital conversion. So we can see here that at the top, there's a sound wave, a representation of a sound wave, and the analog to digital converter samples it every time interval, very short time interval, and samples exactly where the wave is as it goes up and down. And that translates into a number, into a series of numbers. And you can see in the middle the series of numbers that got sampled by the analog to digital converter. Okay, that's digital information. It gets stored on a disk or in a computer or on a chip somewhere. Eventually, when you want to listen to it, you have to convert it back to analog. So you use a digital to analog converter, which takes those numbers, that series of numbers, and converts it back into analog, which is down at the bottom. A couple of parameters that are important in this process. Digital audio resolution is the graphic number 3. That tells us how many times per second the waveform is sampled. That instantaneous level is measured. And 16, and the number of bits is how precise is that measurement, shall we say. So we can see here that 44 kilohertz, 44,000 times per second, and 16 bits is on the left. Now, if you use the same sampling rate of 44,000 times per second, but you sample each sample with 24 bits, you get greater precision with each of those measurements. Then if you increase the sampling rate from 44 kilohertz to, say, 96 kilohertz or 96,000 times per second with a 24-bit resolution, you will get an even more accurate, more precise representation of that original waveform. And in particular, I want to mention bit depth, that whether or not it's 16 bits per sample or 24 bits per sample, that determines the dynamic range from the softest to the loudest you can hear. Here's a dynamic range comparison chart. First on the left is the dynamic range of human hearing. It's 140 decibels roughly. Within a typical room, you only have about 90 decibels of dynamic range, primarily because of the noise floor. If you're in a room in a house, it's going to have some noise, air conditioning, dog barking, machines whirring, whatever. There's going to be a minimum amount of noise in that room. And if your music is below that level, you won't hear it. In fact, live music is the third item here, and that's got about 130 decibels range. So if you're in an orchestra, you see these dynamic markings of triple P, pianissimo, double P, all the way up to quadruple fortissimo, which is as loud as one can play. And that's about 130 dB. An audio signal, an analog audio signal anyway, can have about the same, roughly, 130, a little bit more according to this diagram, from the electrical noise floor. That is, the electrical equipment that you're using has self-generated noise in it. And when you get above a certain point of dynamics, you start clipping the audio signal, and that causes terrible, ugly distortion. Then I want to talk about the sampling rate. Okay, the important thing about sampling rate, that is the rate at which you take these measurements of the instantaneous level of the wave as it's going up and down, that determines the upper limit of the frequency that can be accurately captured. So remember, we talked about the Fourier breakdown of complex waves, which music is very complex, but it can be broken down into individual sine waves. The sampling rate determines the highest frequency within that Fourier breakdown that can be accurately captured and represented. In fact, the sampling frequency has to be twice the highest frequency in the input signal. Or to put it another way, the highest frequency in the input signal must be no more than half of the sampling rate. This is called the Nyquist frequency, after Mr. Nyquist, Dr. Nyquist, I would presume. And if there is a frequency in that spectrum that's higher than half the sampling frequency, then we get a really ugly, nasty artifact called aliasing, which kind of looks like this. So the red waveform is the intended waveform. But if the sampler is sampling, if that's higher than half the sampling rate, then the device that's doing the sampling is going to sample these blue dots. And they're not following the original waveform, they're following a lower frequency waveform. They're getting fooled, in other words, into thinking, oh, this is a low frequency that I'm sampling. Well, it's not. This is called aliasing, and it's very audible, and it's really ugly. So all the frequencies that are being recorded or being represented by the digital audio system have to be no more than half of the sampling rate. So this is going to become important here in a bit. So let me continue on here. So CD audio. We all know CDs. Don't buy them anymore, but we all remember them, I think, right? I certainly do. They have a bit depth of 16 bits and a sampling rate of 44.1 kilohertz, or 44,100 samples per second. Now, 16 bits translates into a dynamic range, a theoretical dynamic range of 96 dB, and a frequency range up to 22.05 kilohertz. Now, modern digital audio conversion technology can't reach these theoretical maximums, at least not the dynamic range. Can't quite reach 96, but it gets close, 92, 93. And if we look at graph number 4 again, we will see that the dynamic range of human hearing is around 140 dB, and a typical room is around 90 because of the noise floor. So 90 dB for a dynamic range would seem very good. That would cover the entire range of what you can normally hear in a room, which is one reason why the creators of CD decided to use 16 bits. And why use a sampling rate of 44.1 kilohertz? Because the highest frequency that it can represent accurately is 22 kilohertz, we'll call it, 22.05. Now, humans have a theoretical upper limit of 20 kilohertz for what they can hear. And really, adults can't hear that high. Only really babies can hear that high. Once you become a teenager and gone to a few rock concerts, that's it. You're not hearing 20 kilohertz anymore. So CD specs should be entirely sufficient to capture everything we can hear in a typical room. But many critics of CDs, as I said before, call that sound, they describe it as cold and harsh. So what to do about it? Well, one thing to do is to increase those specs. And that's where we get high resolution audio in an effort to improve the sound quality of digital audio. Typical specs for high resolution audio are 24-bit bit depth, which gives us 144 dB dynamic range, and a 96 kilohertz sampling rate, which gives us a 48 kilohertz high frequency limit. Some HRA tracks use 24 bits, but at 44.1 or 48 kilohertz sampling rate. So they don't give us higher frequency response, but they do give us more dynamic range. Is that important? I'll give you my opinion in a minute. In some extreme cases, you can buy high-resolution audio tracks with 32-bit resolution. That's 192 dB of dynamic range and 192 kilohertz sampling rate, which is a 96 kilohertz upper frequency limit. Can we hear that? No, we cannot. No one can. Dogs maybe, but not humans. Now, one problem with this is that these changes, if you can hear anything, it doesn't matter. They will not be reproduced unless the audio system that you're playing them on has the capability to reproduce those really high frequencies and that really wide dynamic range. Also, your listening environment has to be super quiet, or you're not going to hear that dynamic range. So you need to be in a recording studio or a purpose-built listening room that has really super good soundproofing. And even then, I think that the improvement is subtle and not super impressive. I've even heard of some companies putting HRA, high resolution audio systems, into cars. Now, this is ridiculous because you're in a car. There's road noise. I don't care how expensive the car is or how much it's insulated. You're going to have a very high noise floor in that car. You're not going to hear the dynamic range of high resolution audio. So there's no point whatsoever to putting a high resolution audio system in a car. I will say that any benefit is probably going to be more evident on headphones, good headphones that can reproduce above 20K and have a really wide dynamic range because they isolate you from your acoustic environment. And I have heard more of a difference with high resolution audio on a pair of really good isolating headphones over ear with good seals around the ear. There you can hear a difference in the high resolution audio. In addition, I'm going to say that most benefits are going to be secondary. With higher sampling rates, you can represent higher frequencies. You can't hear them, but with all digital audio systems, you have to have a filter on the input that filters out all frequencies above half the sampling rate. Remember, we talked about the Nyquist frequency. So anything above the Nyquist frequency that's coming into the system that's digitizing, that's got to be removed. Because if it's there, then the digital audio system will try to digitize it and you'll get the aliasing artifacts. And in a CD system, that filter has to be very steep because you have to let in everything up to 20K and have everything gone by 22K. So it's a very steep filter. If you're sampling at 96 kilohertz, for example, you can have that filter be much more gradual. And that leads to fewer phasing artifacts, which may be possibly part of the reason that some people call CD audio cold and harsh. So if you have a more gentle filter on the input, you don't get those phasing artifacts. Another possibility that I've always considered is that those ultrasonic components above 20K that could well be in an audio signal, if you can reproduce them, they will interact with each other, producing what are called difference tones that do occur in the audible range. So I think this is a possible reason why, with the right playback system, you can hear the difference and maybe experience it as sounding better. Another potential benefit, which has nothing to do with HRA by itself, is that high-resolution audio tracks are often remastered from the original. So if you mastered it for CD, you mastered it for CD, there it is. If you then master it for high-resolution audio, you may very well maybe get a different mastering engineer, or maybe the mastering engineer learned something between the first project and the second project, whatever. It may very well be mastered differently and sound better that way for that reason. So I just wanted to conclude this episode by mentioning an experiment that I did close to 10 years ago. I did an informal experiment on AVS Forum with the help of Mark Waldrop, who was the founder of AIX Records, which made a business of offering high-res audio tracks that you can buy online or you could buy on Blu-ray. And he always recorded in 2496, 24-bit resolution, 96 kilohertz sampling rate. So he provided 3 tracks to me. One, a guitar track by a guy named Lawrence Juber, a jazz trumpeter with combo, guy by the name of Wallace Roney, and a track by Steve Torme, son of Mel Torme, from his album Torme Sings Torme. And he was singing On the Street Where You Live, classic tune. Wallace Roney track was Just My Imagination, and the Lawrence Juber guitar track was called Mosaic. Okay, so he recorded those at 2496, and he gave me 2 versions of each track. One at 2496, and one that had been downsampled to 16-bit 44.1 kilohertz, same as a CD. And I allowed AVS Forum members to perform a little experiment. Informal, not scientifically valid. I will say that right up front. But if we take a look at the analysis, the graphic analysis of these songs, you can see in the upper right, the yellow line is the 44.1 16-bit, and you can see how it just drops off quickly right at 20 kilohertz. That's what I'm talking about, that really steep filter. He had to filter everything out above 22 kilohertz. The red line is the content above 22K. And it goes all the way out to 48 easily. And we can see that in all three of the tracks. Here's the next one, and the third one is very similar. So I took these three tracks, two versions of each. I labeled them A and B. And I flipped a coin to see whether A was going to be the high res or B was going to be the high res. And the other one obviously would be the CD tracks. And I put them on the website, on AVS Forum, and I invited people to download them. And I said, listen to them, play fair, play nice. Don't put them in your computer and look at the spectrum, because then you'll know. But tell me whether you think A or B, in each case, is the high-res audio track. Also, tell me what system you listen to it on. Tell me the player. Tell me the preamp and amplifier and speakers. Or if you were using headphones, what headphones? Because I wanted to see if you listen to it on a high-res capable system, would that make a difference? So we got in, I forget how many, 50 or 60 responses. And Graphic 9 will show us correct identifications by track. So here are the three tracks. The blue bar is correct identification by those who have a high-res audio capable system. The red bars are those correct identifications for those with a non-high-res capable system. And as you can see, the non-high-res capable systems are roughly around 50%, a little less for Just My Imagination, a little more for Mosaic, slightly less for On the Street Where You Live. By contrast, the high-res capable systems came in more around 80% correct. So the non-high-res systems were 50%, which is consistent with random chance. You know, you flip a coin, which is which. But the high-res capable systems did come in better. So they could hear more reliably the difference. And in fact, many of them reported, they said, well, I like the HRA, the high-res track, better. Now, admittedly, this was not a scientific test, and I'll be the first to admit that. But it does suggest that listeners can hear a difference in high-resolution audio files when played on a high-resolution capable system. But unless you have such a system, high-resolution audio is not worth the extra money. So there you have it. For more info on these tests, we've included a couple of links in the show notes that you can go back and read the original proposal and the results, which I go into a lot more detail. As I said, that was about 10 years ago, but I still find it fascinating. So, and I hope you do too. So here's the point of the show where I say, if you have a question for me, I do hope you will send it to htg@twit.tv. I look forward to reading them and answering as many as I can on the air. Maybe you have a question about high-res audio. I'd love to talk about that again. And as always, we thank you for being a member of Club TWiT, which supports the entire TWiT network and Home Theater Geeks in particular. As a member, you can come into the Discord and watch us make the show live, which I do hope you will do. Until next time, geek out.